Today, we will have the pleasure of listening to 4 presenters. The abstracts can be found in the link to join the meeting. The first presentation will be by a master student, Kenneth Duran, who's working for Dr. James Lee, and his topic will be the robotic forming and bending of aluminum sheets for fixed-wing drone manufacturing. Kenneth will have 15 minutes uninterrupted for his presentation, and then we will take some questions. We're going to have to try and keep everyone basically on time, so hopefully we can make up some of the lost time that we had starting this meeting. With that, Kenneth, whenever you're ready, the floor is yours.
Yes, sir. Hello, my name is Kenneth Duran. Thank you, Dr. T, for the intro. I'll start with my presentation now. This presentation focuses, as Dr. T mentioned, on the robotic forming and bending of aluminum sheets for fixed-wing drone manufacturing. The agenda for this presentation will be the problem statement, the state-of-the-art and benchmark, methodology, experimental results and discussion, followed by a conclusion and perspective. So the problem statement. The problem that this research project is attempting to address is adaptive drone manufacturing. So this process that I'm working on stems from a process called incremental sheet forming, which uses robotics to incrementally form sheets of metal, specifically aluminum, and now they're starting to work towards titanium. This process allows for a greater degree of geometric freedom, and it removes a great need of custom tooling requirements from the metal forming process. This process is classified as a disruptive manufacturing technology. It aims to use artificial intelligence, adaptive manufacturing, robotics, and simulations to guide the process and disrupt the current manufacturing paradigm. It aims to do that by allowing for greater flexibility of parts, as well as allowing a manufacturer to manufacture custom parts on demand without the need for the design of tooling. Combining this new method with technology such as additive manufacturing will allow for greater possibilities. Now on to the state-of-the-art processes that this draws inspiration from. The main process is called roboforming or incremental sheet forming. There are a couple different types. One method uses a single point, which is called single point incremental sheet forming. It is shown there on the left. You can use just a robot with a tool. Some manufacturers might have a sort of die or supports that they can adjust the height of to allow this tool to go, press against, and generate the shape of the part they want. The more advanced form of this is double point incremental forming, which is in the middle. And instead of having supports or some kind of a plastic thing that they insert, they'll just have two robots, one from each side of the material. One kind of pushes up as a support, and then the other acts as the workpiece. And then on the right-hand side, there's a close-up view of a part made by this process. And you can see that there's a lot of like layer lines, almost like if you're 3D printing. So this part will incrementally form a part sort of like 3D printing, except it's plastically deforming the material kind of millimeter by millimeter, one little layer at a time, and you get that sort of rough look to it. There are some limitations with these prior approaches. The first being that they are very, very slow. It can take hours upon hours to make a small part. They require massive robotics. They have very complex path planning and controls and sensors. A lot of these sensors and control systems are proprietary, and the tool coatings and such on the tooling used, even though it is minimal, is also proprietary. These parts produced tend to have very rough surface finishes and great dimensional inaccuracies. So to compensate these inaccuracies in surface finishes, they routinely manufacture an oversized part and then cut out the desired size and finish it as needed. The benefits to this process, as mentioned before, are the toolless manufacturing. So even though this is a bit slower, for small cycle productions, if I need something like maybe 100 parts, it might be financially beneficial to go this process instead of manufacturing custom tooling like a die or a mold, which is very expensive. It might take months to design and trial and error until it gets right, making certain parts prohibitively expensive to make via traditional processes. Now, the methodology for my research project is a combination of robotics and off-the-shelf components. One key thing that we aimed to do with this was, again, reduce the need for custom tooling. So all of the robots and materials you can buy are common. Nothing is really custom manufactured. I'm making use of an ABB IRB 6700 industrial robot, using a lodestar pancake sensor, some aluminum extrusions, conveyor rollers, and common hardware. With the exception of the robot, everything I am currently using can be purchased off of like McMaster Car or those types of websites, and used to construct this cell. Now, for our simulation setup, we're doing a simple geometry that replicates the support rollers, the sheet of metal, and then the load roller that's fixed to the robot. The LX represents the sheet metal length, LY is the thickness of the sheet metal, LZ is the width of the sheet metal, DC is the diameter of the load roller, which is on top and will be supplying the force to deform the sheet metal. S is the separation between the support rollers, and then X is the separation between the load roller and one of the support rollers. And these are the material properties. So I will be using 6061 T6 aluminum alloys, since that's very common in use for components and aerospace. Since this is for drone applications, again, I want to use common materials. I stuck with that. And then these are the properties for the stainless steel rollers I am implementing. It has to be much harder than the aluminum in order to plastically deform the aluminum without being damaged. On the bottom right is the isotropic hardening curve that I am using in ANSYS to base the deformation simulations off of. Now our applications and results. So here I am showing simple 3-point bending, and I'm using a simulation of ANSYS, and it's going down and plastically deforming it up to 35 millimeters. And what we're showing here is the steps in this process, showing how there is some elastic recovery inside of the material. In metal forming, this is known as spring back. On the right-hand side, you'll see a mapping of the displacement for each step, and then you'll see the 3 steps on the right where it finishes its elastic recovery and stays stable in the relaxed position. Now, one thing that we would like to do in this study is leverage the use of AI. So implement some of these simulations and models to train an algorithm to help us predict metal spring back so that we can predict the pathing needed to create a final part. So here, spring back compensation is defined as delta Y. That's the difference between the displacement, the capital UY, and the relaxed displacement. So the capital UY is the displacement when this is under a load. That is when the roller is pushing down. When the roller returns, removes the load, it goes back to the relaxed configuration. On the right side, you'll see the black is a deformed, the blue is the relaxed, and then that red is the spring back. So that's the amount of elastic recovery that happens once the load is removed. And that is important in forming a part, because if I want a part to be in the shape of that blue line, I have to overbend it. So the goal of this is to use this as a baseline to train a model to tell us how much to overbend to reach the required geometry that we would like. Now, what we're finding is that this spring back can vary greatly depending on the roller diameter, the support roller separation, the thickness of our sheet metal, imposed displacements, as well as the distance between the loads and the supports. Now, here on the left, you see relaxed displacement and elastic restoration as functions of the actual imposed displacement. What we're doing here is just seeing how much this deflects based off of the initial deformation. Now, higher values of initial displacement lead to higher values of the recovery and the spring back there. However, the actual spring back is kind of constant with those values, in the sense that the ratio of spring back based off of the value is kind of consistent. Another thing that we're measuring is the actual von Mises stresses as functions of these displacements. We need to know this process because that's that's one of our failure mechanisms. We use that to predict if the part that we're trying to simulate and make will break due to the actual forming process. So we want to keep that under that 310 megapascals, which is the ultimate strength, to ensure that there's no material failure happening. Now this here shows relaxed displacement and elastic restoration as a function of roller diameters. And then we also graphed von Mises stresses as a function of roller diameters. What we've found is that the roller diameter doesn't have as much of an effect. It does have an effect, but for these diameters, the differences in diameters are not enough for us to measure significant differences in the amount of spring back that this material is undergoing. To overcome this, I will eventually try to get much smaller, much larger diameters to maybe exacerbate this property and see if I can induce greater changes that can be more visible to understand that connection a little bit better. But even throughout this, again, that maximum stress remains constant and it's under that 310 threshold that I talked about. Here, again, these are von Mises stresses as a function of roller separation. So this is actually graphing how far apart those two support rollers are. Now, for larger roller separation, the plastic deformation is negligible, meaning that larger separation between rollers increases greater spring back without actually plastically deforming the material. Putting these rollers together causes much higher plastic deformation. Now, the maximum stress drops approximately 65% as the roller separation increases from 12 inches to 18 inches, meaning that the closer these rollers are, the greater this stress that the actual material experiences, leading to more plastic deformation. One thing that does have a very significant value is the effect of sheet metal thickness. We found that the displacement increases, your spring back decreases with the thickness of your metal, meaning that thinner sheets have much greater spring back and thicker sheets of aluminum have much greater plastic deformation. This makes sense because a thinner sheet has less material to actually plastically deform, while the thicker sheet has more, allowing for a greater deformation. The thinner sheets are also subjected to at least 30% less von Mises stresses. This is likely due to the amount of plastic deformation happening since it's all going back into an elastic recovery within the material. Now, another one that did have some interesting results was the distance between the support and the load. So in the first slide, that X distance between the actual load roller and the support roller does have an effect on displacement. So it was maximum when X was about 3 inches from the deformation roller. However, the spring back shows identical trajectories in 3 and 6, even though it's off-center, meaning that the spring back direction is the same. So moving this away doesn't exactly change the orientation of how these things are working, so long as it goes up and down. The residual stress, again, here was actually lowest at X equals 6 inches, meaning 6 inches away from this support is where it was lower. Right next to it, it experienced a much greater stress. Another thing that I've been looking into is the effects of repeated loading, meaning that if I have a displacement of 0, 45 millimeters, 50, 60, what happens if I, displace it a small degree, remove the force, displace it more, remove it, and keep displacing it? Now, in order to ensure consistency, I had to do some consistency checks within the simulations. So one way to verify that the simulations are kind of making sense, sort of sanity check, was that the trajectory of these displacements and springbacks remain identical respective of the number of deformation steps. So if I have 5 steps or 100, As long as these directions are staying the same, that means that the simulation is working correctly, regardless of the speed or the amount of steps. Another one is the increment and the number of elements along Ly. The trajectory, again, remains insensitive to these changes. So if I increase these number of increments, decrease them, these things should be the same. They are, which means that these simulations are being executed correctly. On to my conclusions and perspectives. So we've concluded that there is a good amount of relationships between these properties and the springback of this model. However, we would like to expand upon this by employing a multi-scale model to describe the behavior when it has been heated up. So aluminum, in order to form it to more extreme shapes, we want to kind of warm it in some fashion. And in that case, we need to employ a multi-physics model that will allow us to interpret that behavior of warming in conjunction with this. I also need to complete experimental validation of these simulations once the robotics in the lab that I am using have been officially commissioned to actually go and verify that real life matches these simulations. If there's an issue or discrepancy, we can go back and forth between them until these problems have been addressed. And that concludes my presentation.
Well, thank you, Duran, for this interesting talk. And I'm opening it out for any questions from the audience. Anything you want to ask? Duran, you might want to keep your presentation on in case somebody wants to allude to any of those pages. So I'm going to get it started in case, you know.
Yes, sir.
Yeah. So I saw that, and some of it, a lot of it makes sense, you know, with the thicker and thinner sheets.
Yes, sir.
So this is the question is like, how do you train the machine to understand? I mean, are you gonna do it like based on thickness? It's gonna know like when to over deform, because if the thinner sheet has more spring back, right, you need to deform it more if you want to, you know, if it has a spring back to get the shape, right, versus a thicker one, not so much. So
yes.
So how are you going to train that model to be able to understand the differences in thicknesses, and what is that cutoff? Is it a linear relationship? Is it you know, a more complicated relationship? And again, when you add the temperature, that adds another layer of complexity. But how are you planning to get training data if that is an AI model?
Okay, so I have a bunch of samples that I actually plan to go and bend and then put this data into a machine learning model that somebody else is helping me work on. Okay. I need to get approval from facilities to turn these on. We have the stuff set up. We just need their electrician to come by and give us the go-ahead to start the experimental validation, which I mentioned towards the end. I need to actually experimentally validate this. That will involve me going and running a bunch of tests, getting some data, feeding that in. And then there is actually a relationship between the sheet metal thickness, like you're saying. There has been literature and work done on this, and it's a relationship between the sheet metal thickness and the maximum bend radius that you're allowed to achieve. So it would be a matter of putting that into this model, putting that bend radius relationship to the thickness as kind of the limiting constraint of saying, based off of this thickness, I cannot exceed this radius, and then performing a bunch of results. These are very simple 3-point bending. I want to do some stuff with flange bending, and eventually incorporate your multiphysics and rolling. So this is just the first baby step in a much bigger, somewhat more ambitious process.
Great.
Do
we have any other questions?
Question?
Go ahead.
Yeah, may I ask a question? Thank you so much. Sorry, I don't know anything about this kind of manufacturing, so please bear with me for a second. So 2 questions. One is, why do you actually need to bend like an actual material? Why don't you use something like finite element to generate more samples if you're running a machine learning approach? that might help you get more data. I don't know if it's feasible or not, so that's why I'm just suggesting it. And then my second question, which is sort of relevant, is so there's been a lot of discussions in the car manufacturing. After Tesla Cybertruck started bending steel to make it. To make the cars, and then there's a lot of discussions that I hear from the auto manufacturers in terms of they're moving towards that direction. So, and how does this translate to that scale of manufacturing? I'm just curious to see how does contribute to that.
Okay, yeah. So for the first question, can you repeat the first question again, sir?
Yeah, I'm just trying to see if how can
okay, yes, you mentioned that
use like finite element, yeah.
Yeah, okay, so we're doing some finite element analysis with this. I want to do experimental results to validate those finite element analyses, just to make sure that everything I'm doing in ANSYS is true to real life. And then, like you're saying, we can do all of the intermediate steps. Like, let's say I do 30 millimeters, 40, 50 in terms of displacement. I can do ANSYS, like you're saying, for all the intermediate steps to have more data and feed in. But at least for some of the major testing, I would like to experimentally validate that just to ensure that it's working out correctly. If there's an issue in my simulation that doesn't match what's happening in real life, I can go back and correct that. That way, all of the data that I'm feeding into this model is accurate and consistent. To the second question, in terms of usage in auto manufacturing, this type of a process is good in the sense that if you want to, for example, change the design of a part, I don't have to completely reconfigure my tooling. I don't know if you've seen how they do stamping processes where you have a gigantic press with some dies and then you put your sheet in there and stamp it. These are extremely large machines. They can take up, an entire room. It only does one task. And then if I want to change the part ever so slightly, I have to go back, retool, reconfigure the actual molds themselves. These are very hard metals. They're hard to machine. They're expensive. They can cost tens of thousands of dollars for a single mold. So in this sense, if I use this process, I don't have to reconfigure a mold. I just put a new file into this algorithm and it starts forming the part. This also allows for a sort of decentralized manufacturing process. So instead of having all of my raw material, labor, everything be in one gigantic factory, I can put, a robot in something the size of a shipping container and have it turning out parts. Not necessarily that you want to do that, but I can have a factory with a much smaller blueprint making parts, say, for a region instead of one gigantic factory making parts for a continent. This can help make your supply chain more robust in the sense that if there's something happening in this area, well, I have a bunch of smaller factories that are not necessarily influenced by a material or labor shortage or weather or something like that.
Well, I would like to thank Kenneth for his presentation. I would like to keep us moving so that we can keep on time. But thank you very much, Kenneth. And if you have any other questions for Kenneth, please reach out to him. You can easily reach out to Kenneth, send him an email. Kenneth, please put your email into the chat in case somebody wants to reach out to you with any questions.
Yes, sir.
With that, I want to move on to the second presentation of the day. And Gabby Gutierrez, a doctoral student working for Dr. Gasser Ali, will be providing a presentation on modeling the impact of extreme weather events on the U.S. rail network. With that, Gabby, please show your presentation and you can proceed when you're ready.
Okay. You guys can see this, right?
Yes.
Okay. Hi, hello, my name is Gabby. I am going to be presenting my research. It is a vulnerability analysis of the US rail infrastructure using network analysis, done mostly by me and with the help of my professor, Dr. Gasser Ali, under the CREST, which is run by Dr. Constantine Tarane. So a quick outline of what I'm going to do. I'm going to give an intro and explain my goal, my methodology, how I kind of work through this problem, some results that we've got, and a quick discussion to close it off, and some feature work that we're currently working on. So to start off, the U.S. rail network is a very large network of rails. There's about 140,000 miles of track in the United States, and one of the biggest risks to this is temperature, specifically buckling caused by temperature. Rails, as you can see in this top image, are usually continuously welded. This means that they do not have any expansion joints. So when the temperature of the rail starts to heat up, the steel in the rail will want to expand, but it doesn't have any space to expand. And if this thermal expansion gets too strong, then we get buckled rail, as you see down here. And this can lead to derailments and other types of accidents. So how we find this, or how we figure out if a rail will buckle, is we take the rail neutral temperature, which is basically just the temperature that the rail is considered the most stable, and we will try to investigate when or what the risk of buckling might happen. The reason this is important is because of with the changing climate, there's a lot more probability of heat waves, and they are also getting a lot stronger. All sorts of weather events can happen at any time, and they just get worse and worse. So there's a need to investigate the risk of these rails. So the problem statement and the knowledge gap. Currently, most research is focused on finite element analysis and lab experiments. So basically, they're working with the rail on a small scale, usually in a lab, to try and figure out the point of buckling for the rail. This is fine, but in a real world scenario, there's a lot more factors at play that can affect the rail. Something else that has been worked on is people trying to use machine learning to try and predict the type of accidents in the rail. What they'll do is they'll usually take accident data that currently exists, plug it into a machine learning model, and try and figure out what type of accident was caused. Because of this, there's a need for a analysis on a network scale or a holistic scale, basically taking in the entire network and all sorts of weather at any given points, not just in a lab. So our goal, as I said, is to investigate the vulnerability of the rail network on a large scale against extreme weather events using graph theory and risk assessment. So the methodology, basically, it's a very kind of simple process. We take the rail data, weather data, and county data, and I'll explain more about this in a little bit. We will try and create a weather-informed rail graph. With this, we will try and calculate the probability and the impact. The probability is just the likelihood of failure. The impact is how important is a rail in its position. And with this, we will try and calculate the severity of the rail. So this is the 3 points of data that we got. We took data from the Federal Railroad Administration. There were about 328,000 rail edges before cleaning. We also took data from the NOAA. This is all just weather data. It is monthly data that has been collected since 1986 or 1896. Sorry. So a little over 100 years worth of data to try and feed into our application. And finally, we took some data from the census. This is county data used to kind of put together the previous two data sets because the numbers within them don't agree with each other when it comes to what is defined as a county. So this is our rail, or this is the US rail network. This is all of it before having done any cleaning. You can see here there's a lot of little spots that are kind of in the middle of nowhere. They're not really connected to anything. All of this needs to be cleaned out. So what we did is we just took all the data that was considered main network, and we only use those points. All of these other little branches just kind of disappear after that. We are currently exploring this as a case study. So we're taking 4 major dates. We're taking 1936 as the hottest month, and this is actually a historically bad heat wave. You can look it up. There was a bunch of disasters. A lot of people got injured and or died from heat exhaustion. We're also taking last year in the summer. This was also another historically bad heat wave, one that we've had in a long time. There is a possibility that this year could have been hotter, but at the time that we took this data, we weren't there yet. So we haven't actually analyzed this year. Some other dates that we took were 1934. This was the coldest recorded temperature. And 1977. This is just another historical cold snap. Finally, for the case study, we took a couple of cities. We took Seattle, San Diego, Chicago, Boston, Brownsville, and Tampa. We chose these locations because of the fact that they are considered major ports. So a lot of goods and freight trains kind of come to and fro for these spots a lot. So calculating the probability, it's fairly simple. We just take a normal function of the hot and cold temperatures against the neutral temperature, and we just plug them in. The neutral temperature, I forgot to explain earlier. We are currently making this as an assumption. The actual neutral temperature of rails is usually unknown because there's a lot of factors that go into it, such as the data was constructed, how long has it been since the rail has been laid down, et cetera, et cetera. For the rail neutral temperatures, we're just taking it as the average temperature of the area. The impacts, so to calculate the impact and how important a rail edge is, we just use this formula, or this algorithm, I mean. So first we calculate the shortest path, say from Brownsville to San Diego. We select each rail segment, we remove it, and then we recalculate the shortest path. If there exists a route, we will find the distance of that alternate route and compare the two. If there is not, we will mark that rail as critical. This means that there are no alternate paths between this point and the other if this rail was to be removed. And then we do this for every single selected point, and then we just finish off. The severity is a function of the probability and the impacts. So the higher the probability and the higher the impacts, the higher the severity. In risk assessment, we don't care too much if only one factor is high. Typically, if one factor is high, it's not considered as big of a risk as if both factors were high. So for example, if there was a high probability of something to happen, but it had a very low impact, we wouldn't really prioritize it as much as if two things were medium. So if there was a medium impact and a medium probability for something to happen. Moving on into our results, these are the temperature maps that we got. So we got the maximum temperature of the United States, the average temperature, and the minimum temperature. These are important for our calculations for probability, as you'll see in the next slide. These are the effects of the temperature. You'll notice these areas here, the Northwest, Pacific Northwest, this general area. It is very temperate. This is important for our calculations because it kind of shows that these areas are very likely to fail just because they are very far off from their rail neutral temperature. If a rail gets too cold, then it'll start to crack. If it gets too hot, then it's at risk of buckling. Generally, these other areas of the United States are not as big of an issue, but they still can run into problems of a high difference in temperature. And these are just this is basically what our formula returned. Like I said, this general area is very high risk of failure, just because of how temperate they are. And this is against the hot days, and then here is the cold days. Like I said, temperate areas will kind of fail are more likely to fail. This doesn't mean that these other areas aren't at risk of failure. It just means that they have a much lower probability compared to these areas. Any critical rails that we found, using just these paths, we only really found these areas, the paths from Brownsville going up to San Antonio. Excuse me. Since these rails are critical, that means that this is the only existing path from here up to the rest of the network. And if any of these rails were to go down, then then any trains that are currently here or trying to get into here would not have a path to progress. This could potentially disrupt a supply chain, or just generally delay any sort of goods that are coming in. The impacts, so this is after we had run our algorithm. You'll notice down here, there's a huge lack of alternate paths, especially here in Nevada, Arizona. This having a high impact basically just means that if these roads were to go down, then a train would have to reroute, and it would take a very long time for them to actually reach their destination. So it's very costly for time. There's also a high impact area up here in Seattle. And then finally, our severity. Up here in the Pacific Northwest, in the Midwest, there's a very high severity. Since these areas are very likely to fail just based on their temperature, they kind of have a higher tendency to to have a higher severity. Especially in this area, there's not a lot of alternate paths. Generally, there's not a lot of alternate paths between going from the east side of the US to the middle. So it kind of results in this. And I'll zoom in on these maps so you can see them a little better. Go. And then during the cold days, still in the Pacific Midwest, there's a high severity. There's also a very high severity in this general area, Illinois, around there. These areas do get very cold, and as such, they're likely to crack, which is basically just the rail gets too cold and it'll kind of pull itself apart. And here's the map zoomed in again. So our conclusion, what we have found is that some areas of the network are particularly vulnerable, especially the Midwest and the South. A high difference in temperatures kind of increases the probability of failure. Having many alternate paths will reduce the impact of rails. And severity analysis is very important for planning the future of the network. This sort of decision tool can kind of be given to a decision maker to kind of help plan out like what areas need maintenance, what areas could use a new path. Typically, if you did not know the current state of the network, but if you were to plug in, say, the next few days, you could try and figure out, is there a probability for something to happen over the next few days? Some future work that we want to do, we want to add other weather events. Ideally, we would add things like flooding and storms. We would like to improve the probability function. Currently, we only tried out a normal distribution. We're wondering if there are any other formulas that can kind of do better than just this. We also want to add in some other factors. Currently, we just have temperature. But like I mentioned at the beginning, there's a lot of factors such as humidity, exposed sunlight, shading, etc., etc. And the last thing that we want to add is traffic data. there's a lot of traffic that goes on in the rail network, but we don't really have access to data to kind of try and add that into our shortest path formula. We want to acknowledge the UTCRS and the CREST MECIS for their funding. Any questions?
Well, thank you, Gabby, for the presentation. I want to start with the audience. Alireza, I'm sure you have some questions. Okay, I will get it. Diego, you can go ahead, and I have some questions after.
Hi, Gabby.
Hi.
So my only question is, what is the assumption that you guys are doing for the neutral temperature? And I might have missed it, but what is how are you guys using the neutral temperature in your formula?
So the neutral temperature, currently we are just assuming it as the average temperature. So essentially it would be this map here. In reality, the real neutral temperature is usually around maybe like 80, 90 degrees. I believe when people lay down rails, they choose to do them on days that are particularly hot. So that way, whenever it gets too hot, their neutral temperature is kind of already adjusted to this. But data like this isn't really publicly available. So we kind of just have to make the assumption that it will be the average temperature in that region. And we're using it with this formula here. So we take the neutral temperature and then we just do a little bit of math to it as a normal distribution.
So I imagine the neutral temperature changes like monthly or seasonally. Are you guys taking that into account?
This is just an example distribution. This is for one day at one time. This model can actually account for any day at any time.
Okay.
Essentially.
Diego, the real neutral temperature does not change. The real neutral temperature, when you lay down a rail, you basically do it based on people study, the weather in that area, right? And they pick an RNT that they feel is the most appropriate. So not every every area has the same, right? So it's a lot of it is based on understanding your network and your rail and the weather and all of that. Now sometimes you can have extreme weather conditions where like even though you lay it right, like in the Midwest, you can have like huge variations. Like one day it could be -20 and the other day 60, right? So you can have huge swings. But again, the rail it's not that RNT changes. It's how you set your rail. But that brings me to a question, Gabby, is like I'm looking at this, right? And a lot of it, is intuitive, meaning like a lot of the stuff that you presented, okay, makes sense. I would have like gotten to these conclusions, without a model. Like it's from looking at a lot of literature and all of that familiarity with this. I can tell you, like, whatever your conclusions are, well, some can argue it's obvious, right? So what is your model doing that providing information that is not obvious? And have you done a literature review to see what other work and other models have been going on in this, right? Because and how does your model differ from what has been done?
Well, to answer that first question, this model is adjustable. I did kind of briefly touch on it, that you can just plug in any day at any time to try and give you back the severity. But another thing is that people aren't actually doing anything like this. As far as I could tell, nobody is trying to make a graph model of the rail network. And in addition to that, this is kind of just like the baseline for what we have planned in the future, which is to kind of expand on this model and make it a much more configurable application for decision makers. Does that make sense?
Yeah. Any other questions? We have time for questions. Please, if you have any questions, just raise your hand.
I have one question. Sorry, I fixed my microphone.
Great.
So you talked about prediction and all of that based on data and everything. Is there any real-time assessment of these going on? Are there any sensors that can detect any sort of potential derailment, like anything like that in real time as the train travels over the rail? Because you assume these don't happen right away. It's just some sort of a gradual process of like eventually to getting to a point that it's becoming dangerous.
There are methods in place currently. We have things like hot boxes and sonar detectors, I believe they're called. They kind of try and figure out if a train might have problems while it's going on the rail. The problem with these methods is that they're not preventative, they're reactive. There was a case in East Palestine recently, I believe last year, where a train went over a hotbox and it caught fire, and nobody really noticed until like 100 miles later.
But Gabby, I want to stop you there because again, that one had nothing to do with track, right? That one was a bearing, right? That was bearing related, nothing to do with track. I think the question is more like, you know, is there something right now that can look at track and see the potential of it buckling, right? I mean, because that's what we're trying to do is what are the areas that are more likely to buckle and cause, you know, issues so that people can, you know, that the crews or the railroads can go in and say, hey, potentially this could be an issue if we have this extreme weather, so we need to be on the lookout, right? I mean, those are things that, again, it's not an exact science, right? You set the R&T based on, you know, historical data, and you say, hey, over the past 10 years, this has been the weather in Lincoln, Nebraska, right? So you go and say, okay, what is the best R&T for this area? Now, you could have extreme weather conditions that do not take that average into account, and then all of a sudden you have issues. So the question is there something right now in field that can potentially spot this?
From all the literature review that I did, I could not find anything like that.
Okay.
There might be some models out there, but I couldn't actually find any when I was trying to research this topic. I did mention also before, a lot of these experiments that involve finding the like buckling temperature, they're usually in lab and not out in the field.
So one of the things I would like you to do, so we have access to people at BNSF and MXV Rail. So Stephen Wilk is an expert in rail buckling. I mean, he has seen it all. And Adam Bankston is our BNSF contact that is helping us. We might have you schedule a meeting and talk to them and just discuss your model with them and see if there is something, because they're part of a rail, class 1 railroad. So they might have some input for you and Dr. Ali, and see how the model can be, you know, kind of fine-tuned to be able to help the class 1 railroads and the rail industry.
Yeah.
So, Konstantin, I just want to I brought this up because I was talking, you might be interested in discussing with them. If you don't mind, I'll put you in touch with them. There's a few of these companies that do now autonomous rail system, autonomous freights.
Mm-hmm. And
one of the topics that they were discussing was essentially the safety of the rail. Is it suitable for the they automated train cars, not the locomotives. So the question was, is it safe for that particular sort of train car? So they might be interested in learning more about what you guys are doing.
Mm-hmm.
So if you don't mind, I'll send an email. I'll introduce you to each other.
Yeah,
I think they would love that. So to hear more about it.
Thank you, Alireza. I appreciate that.
Okay.
Well, with that, I want to thank Gabby for the presentation. and we're going to move on to the third presentation. And our third presenter is Chenwei Huang, doctoral student. He's working with Dr. Alireza Talebpour from University of Illinois at Urbana-Champaign. His topic will be multi-depot capacitated K-Chinese Postman problem for UAV patrolling. With that, I would like to have the presentation on, and you have the floor whenever you are ready.
Hi, can you guys see my screen?
Yes, you're good.
Okay. Hi everyone, my name is Chenwei Huang. I'm a second-year PhD student at UIUC. Thank you for allowing me to present at this webinar, and I appreciate you guys taking the time to listen to this presentation. So in this presentation, I'll be going over the multi-depot capacitated K-Chinese Postman problem for UAV patrolling. And this research was done under the supervision of my professor, Professor Alireza Talebpour. So yeah, just some background information here. Traffic safety and congestion continues to remain a worldwide transportation issue in our transportation systems today. Current patrolling measures have been utilized to mitigate these issues. However, they are ineffective. But with the introduction of UAV technology, this provides an alternative strategy to patrol the networks here, especially in large-scale systems. So yeah, most of the current UAV patrolling work have formulated the problem using a node-based formulation here. However, much of the work here do not consider arc-based formulation here, which aims to cover edges of the network, which may be more applicable for UAV patrolling applications. So yeah, most of the current arc routing work is widely applied in applications such as mail delivery, garbage collection, and road maintenance. However, as I just mentioned here, a lack of attention is given to modeling the patrolling problem as an arc routing problem, specifically as a K-Chinese Postman problem here. So yeah, just to introduce the problem here, the K-Chinese Postman problem is a variant of the traditional Chinese Postman problem. Here, the K-Chinese Postman problem introduces a constraint that we must generate K sets of least cost walks such that all the edges in the network are covered at least once. And because here we have this specification on the K walks here, this problem is NP hard for situations where K is greater than 1. So yeah, just to give some brief introduction on the existing methods to solve the problem. One method proposed in this work here proposed the exact method. However, in their method, they only found the results to be solvable for small-scale instance graphs, but cannot generalize to larger graphs here. As a result, because of the scalability issue, most of the works have proposed heuristic approximations to solve the problem. Notably, these two works here. Yeah, however, the heuristic works proposed previously to solve these problems do not consider two important considerations that may be very important in applications like UAV patrolling. Specifically, the first limitation is that it assumes that walk capacity can have infinite capacity. So as a result, walks generated may be of infinite capacity, but which can be impractical in real-world situations. For example, where UAVs may be capacitated by their battery constraints. Yeah. Secondly, a second key limitation that is overlooked is that those previous works assumes that only one depot node and location is sufficient enough for the operations. However, this produces suboptimal solutions. For example, in a situation where edge of interest to be covered is very far away from this specific depot node. As a result, the walk generated in order to cover that edge may be very lengthy. So yeah, as a result, in my study here, I propose to incorporate these two considerations here into my problem. Specifically, the new assumptions is that I allow multiple depot nodes. Depot nodes can be placed at different locations along the network. We also introduce a new energy weight on top of the cost weight here, which is associated with the walk capacity constraint here, which corresponds to the UAV battery capacity. So overall, from this, we formulate our problem as an integer linear program. And to address the computational complexity and the NP hard nature of the problem, we develop a heuristic framework that does these sets of tasks. So yeah, here are the notations used in the ILP formulation here. The NKD here is a binary variable which indicates whether walk K selects node D as its depot node. YD here is also a binary variable which indicates whether node D is chosen as a depot. XKIJ here is also a binary variable which indicates whether edge IJ is chosen to be included in walk K. CIJ here corresponds to the cost of edge IJ, which in that patrolling application could correspond to the flight time or distance required to traverse that edge. BIJ here corresponds to the energy costs of edge IJ, which corresponds to the battery consumption here in the patrolling application. Capital B here corresponds to the maximum walk capacity for each of the walks K. Yeah, UKI here is an integer variable, which represents a positional variable of each of the nodes in the walks. So yeah, this just shows the ILP formulation here. Overall, our main objective is to minimize the total cost generated among all the walks, as well as the total number of depot operations utilized in the network. Constraints 2 and 3 here specifies the depot selection constraints. Specifically in constraint 2, it specifies that for each walk K, it must choose only one of the depot nodes as its starting and ending point. Constraint 3 here specifies that for each of the walks K, it can only select among the feasible set of depot nodes, so where YD is equal to 1. Yeah, constraints 4 and 5 here specifies that for each walk K, the number of ingoing edges and outgoing edges out of the depot node must be equal to 1. Constraint 6 here specifies the flow of conservation constraints for all the non-depot nodes in each of the walks K. So the number of ingoing edges for that node must equal the number of outgoing edges for that node. Constraint 7 specifies the edge coverage constraint. So for each edge in the network, it must be covered by at least one of the walks. Constraint 8 here specifies the walk capacity constraint. So for each of the walks K, the maximum energy consumption must not exceed the maximum capacity allocated for each of the walks. Constraints 9 through 11 specify the subtour constraints. So yeah, as mentioned earlier, I propose a novel heuristic framework to solve this problem here. Specifically, in this framework here, I have 3 main algorithms that work together to conduct these sets of tasks. Here I will give a high-level idea on all the algorithms here. So the first algorithm is a walk generation under constraints algorithm. And as indicated by its name, the main goal here is to generate a set of energy capacitated walks such that all the edges are covered at least once. So here are all the steps that highlight this algorithm here. So we first initialize our process by sorting all the edges in descending order by their cost. And subsequently, we then perform a iterative procedure here, or from this sorted set here, we determine whether that specific edge is covered by any of the existing walks that we generate. If it's not, it's an uncovered edge. In that case, we repeat steps 3 through 5 here. Specifically in step 3 is a walk generation process, where we generate a set of candidate walks from the existing depots, because now we may have multiple depots in our network. And in the case that we do, we then select the least cost walk among each of the associated walks with its associated depot here. And using that least cost walk best, then we do the constraint check here. If that associated walk exceeds the energy capacity B, then we need to conduct these steps to generate a new set of energy capacitated walks in order to cover this edge here. So the first thing we do is that we add a new depot node at one of the endpoints at this uncovered edge here. And we also create an artificial link to connect the new depot node with the original depot node. And then from this, we then generate a new set of energy capacitated walk new to cover the specific edge here. And from that, we choose a walk with the least cost and then add that specific walk to the walk set here. And subsequently, we also update the new depots we added to our overall network configuration. So yeah, algorithm 2 is a depot node setting optimizer. And by this algorithm, the main goal here is to optimize the placement of our initial depot in the network. So there are 2 main steps here to conduct the algorithm. Step 1 is where we initialize our depot location by calculating the central tendency in our network here. Once we've done that and determine our initial depot location, we then run algorithm 1 to generate the set of energy capacitated walks under that configuration here. And from that, we then compute the total cost under that initial depot location. And step 2 is where we conduct the iterative search procedure to optimize our depot location placement. So in order to do that, we perform a hop neighbor search on the current depot location. It should be noted in the first iteration, our current depot location, is just equal to the initial depot location. And from that, we then run algorithm 1 for each hop neighbor to generate the energy capacitated walk associated with each of these neighbor location settings. And from that, if we identify that we have a cost improvement among any of the neighbors, then we set our current depot location setting to the neighbor location that produces the highest cost improvement. Because if we set the current depot location to this neighboring location, then we produce results with a better solution. And if our current depot location also improves upon the cost in comparison to the global depot location, then we update the global depot location to the current location as well. And to terminate this iterative search, one of these stopping criteria is met. Yeah, to terminate that. Yeah, so algorithm 3 is where we utilize the results from our previous 2 algorithms to reduce the total number of walks K and also to balance the energy consumption among the merged walks. So this is a merge procedure here. So there are 3 steps here. Step 1 is where we first initialize by sorting the walks that we generated from the previous 2 algorithms based on ascending order by the total energy consumptions they used. And then subsequently, we then partition the sorted walks into separate sets, grouped according to their depots, because in order to make the merge procedure compatible, we should group the walks according to the same depot nodes they use. Step 2 is where we perform the iterative merge procedure here. So we do that for each of the partition sorted walks that we grouped based on the depot nodes. So from that, we select the first walk and second walk from the set here. And subsequently, we find the splice node position T and walk C such that the energy path connectors to connect node T to the beginning and ending points of H hat is minimal. H hat here is computed by trimming all the overlapping edges that also occur in C. And from this, we then perform the merge operations here. And there are two merge operations in this algorithm here. Operation 1 here occurs in situations where this energy path component and H hat here satisfies the residual energy capacity of walk C, which is calculated by taking the difference between the maximum energy capacity B and the current energy capacity of C. Yeah. And if it satisfies, then we can directly merge the connector and H hat into position node T and walk C. On the other hand, if this residual capacity is exceeded by these components here, then instead we focus more on a coverage-based analysis, operation analysis here. Specifically, here we identify and merge all the one-time coverage edges that occur in H into the splice node position T and C that produces a minimal energy path connectors from node T to the beginning and ending point of that associated one-time coverage edge. And if none of these operations are valid, then we move to the next pair of walks and repeat this procedure again. Yeah, and step 3 is where we finalize our merged walk sets. So because operation 2 here, we can only merge at most one of the one-time coverage edges because of the residual energy capacity. In this case, for all the other remaining one-time coverage edges that we identify in H, we generate a new set of short energy capacitated walks here. And finally, we add our resulting merged walks to the merged set. So yeah, to analyze our performance of our framework, we conduct experiments on both small and large scale patrolling instances here, which are modeled as grid graphs to emulate urban network environments. So here our two edge weights, cost and energy weight, are also varied to reflect different network characteristics. For example, different edges may have different flight time or distance, or may also have different energy consumption. Yeah, so for each graph instance, we also define a specific energy capacity B here, which introduces a degree of constraint tightness on the networks. Yeah, so finally, our heuristic framework is benchmarked against the ILP, Solver, and Jarobi, and the Alchema merge algorithm. So yeah, this just shows the results for 3x3 small scale grid instance here. The above shows the results for our results from the ILP solver here. As you can see, overall, it generates an optimal solution with 4 energy capacitated walks while operating under a single centrally placed depot node here. Here, as you can see, the bottom graph shows the results from the heuristic framework here. Overall, as you can see, 5 energy capacitated walks are generated here. Specifically, here, it should be noted in walk 3 here, the edge of interest to be analyzed was 1, 0, and 2, 0. And because the original depot node 0, 1 here is not able to generate an energy capacitated walk to cover this edge, in that case, we've added a new depot node here at 2, 0 and generate this walk to ensure this associated energy capacitated walk still covers this edge here. Yeah, overall 5 walks are generated under a 2 depot operation setting. So yeah, this just shows the tabular results here. I've not included the tabular results on the small scale instance, but based on those findings, it was determined that the the ILP solution, Jerobi, outperforms all the other heuristic frameworks because it was able to solve those small-scale instances optimally. On the other hand, here, as you can see, the ILP solution on all these large-scale instances becomes computationally intractable here, as it cannot solve the problem. However, the heuristic approximations here offer a much better solution to solve these large-scale problems here. Specifically, as you can see, our heuristic framework outperforms the Ogmer merge algorithm under a multi-depot setting here. Additionally, as you can see, in contrast to the Ogmer merge algorithm, our heuristic framework is able to generate shorter and energy constrained walks, unlike the Ogmer merge algorithm here. Yeah, this shows the potential for our framework to be scalable and effective in large-scale scenarios. So yeah, furthermore, we also evaluate our merge algorithm on the same set of instances. Again, I've not shown the results for the small-scale instances, but based on those findings, we found that performing the merge algorithm on those small-scale instances have minimal impact, as it leads to minor reductions in the total number of walks k here. Additionally, it also results in a moderate increase in the total operational cost. However, as you can see by this table here, the merge algorithm proves to be very scalable and effective for the large-scale instances. Specifically, as you can see, it leads to a very significant reduction in the total number of walks k. Additionally, as you can see by the maximum walk energy consumption and the average energy consumption here, applying the merge procedure is able to balance the energy consumption generated across all the merged walks here. However, a limitation of this is that because we're merging the walks here, it creates walks of longer length here. Yeah. However, it should be noted here, the operation cost does improve here, which can be attributed to the fact that the benefits associated with reducing the total number of walks k outweigh the cons associated with increasing the average length of the merged walks. Yeah. So yeah, furthermore, this just shows the results for a coverage-based analysis for our merge procedure here. So from both our small-scale and large-scale instances, we found that full edge is preserved even by reducing the total number of walks k. As shown here for a large-scale network here, by applying the merge procedure, the low coverage edges follows a similar distribution, to prior to applying the merge. Additionally, as you can see, the merge algorithm also demonstrates a potential to eliminate extreme overcoverage values here. Yeah. So yeah, just to conclude, what are our 3 takeaways from this study here? So first, we have modeled and formulated the UV patrolling problem, considering 2 of the limitations that was mentioned earlier. And we formulate this as a multi-depot capacitated K-Chinese Postman problem. Secondly, to address the computational complexity and NP-hard nature of the problem, we developed a heuristic framework that is capable of conducting these sets of tasks here. And from our findings, we found that the framework is both scalable and computationally efficient for large-scale patrolling instances. Despite this, there are still future considerations that can further improve our study here. Specifically, the first thing we can do is to incorporate different takeoff and landing points or depots associated with the UAV walks into our problem framework and heuristic framework as well. And secondly, we can also extend our framework to accommodate real-time updates and dynamic network conditions. For example, where edge priorities may shift due to changing obstacles or threats, or where energy consumption may also change due to environmental factors. Yeah, this concludes my presentation. Thank you for your attention.
Well, thank you, Chenwei, for this presentation. And I'm sure all of our, drone people here are going to have many questions. So get ready. We're going to start with, so we're going to start with Dr. Chilu Luki. Go ahead. Unmute yourself. And you have, yeah. Luki, are you hearing me? Yeah, if you're talking, you're muted. Let me see if I can unmute you. Okay, Javier, why don't you start until we figure out what...
Thank you. Hello, my name is Cyril. I'm also doing drone work. I was just interested to know how you are, I guess, testing this like through simulation or hardware, and if it takes into consideration maybe like variable energy like consumption, maybe through the use of sensors or anything like that. If there's a spike in energy at any
Yeah,
point,
right now
or...
it's just more of like experimental analysis. Not
Mhm.
So I haven't really considered like using real-time data or a real live network data. Right now it's just based on like a simple assumption here without considering like actual real-time modeling of these parameters here. Yes.
Okay.
That would be a future work. Yeah.
Got it.
Luki, you're next.
Can you hear me?
Yes, we can hear you.
Okay. So nice presentation. And for your work is a kind of optimization of the petroleum or path, the shortest path funding. And my first question is why you use Chinese Postman path planning? Why not other path planning like a TSP or multiple TSP or minimum spanning tree?
Yeah, this is an arc routing problem. So a Chinese Postman problem is a type of arc routing problem here. Those algorithms you mentioned is more like a search algorithm. So because I'm using this because it's, as mentioned, it's very underexplored in this area, specifically related to UAV patrolling. Yes.
And the other question that what kind of simulation about your research? You haven't tested your algorithm on hardware, right?
Right now, this is just generated grid instance. So I generated this myself. Future work can look to incorporate like building a real like network scenario into this here, considering real factors like battery constraints, etc. here. Yeah.
If anyone has a fleet of drones willing to collaborate with us, we would love to work with you. We don't have any drones. We don't have the expertise to run it either. So if anyone is, I know a lot of people, including you, who have that capability. So we would love to explore the collaboration if you're interested in it.
Thank you.
Thank you. Thank you.
Other questions? So let me ask you one question. Can you go to the table you have? And I'm just curious. Okay.
This table?
Yes, this table. I don't see units, so I'm just trying to understand the cost object. Okay. What are those representing?
Those? Okay.
Yes.
So this represents this objective here, the total cost among all the walks, along with the total number of depots utilized.
Okay, so it's a number, right? And the lower the number, the better.
The lower the number, the better. Yes, because our goal is to minimize this function, this objective. Yeah.
Okay. Yeah, I just like was not clear. Okay. Other questions? Any other questions? Okay. Well, thank you,
Thank you.
Chenwei, for your presentation. And as I said, like you might want to, keep the conversation going, and maybe you and Dr. Talebpour can work with Javier and Luki and see, because Dr. Luki there has a lot of robots and ground robots that in his lab that you might want to work together and see how this can. It's very nice if we can have like some joint work and joint publications. That would really look very good for all of us. So with that, like, please, if you need to set up a time to talk, I think that would be a good way to do this.
That's right. That's right. My student, Jose, he works on the task allocation for multiple robot system. Yeah, very similar to your work.
Thank you. Thank you.
Excellent. Okay, so with that, I want to thank Chenwei again, and we're gonna go on to our fourth and last presentation. The student Mario Camarena, who's a master student under the supervision of Dr. Fatemeh Nazari and Dr. Nurzulai, will be presenting. The title is AD-SAM, Fine-Tuning the Segment Anything Vision Foundation Model for Autonomous Driving Perception. With that, Mario, the floor is yours. You can go ahead and get started whenever you're ready.
Okay, great. Can you hear me?
Yes, you're good to go.
Okay. Well, hello, everyone. My name is Mario, and today I'll be presenting our work on AD-SAM. So this project was a collaboration between UTRGV and UC Riverside, and I was advised and supervised by Dr. Nazari and our other co-authors. So just to summarize the project before I get started, we essentially took a powerful vision foundation model, the segment anything model, or SAM for short, and adapted it into a dense pixel-wise semantic model tailored to autonomous driving road scenes. And along the way, we addressed 3 persistent issues in AD perception. So what is image segmentation? In short, segmentation is a way of cutting out parts of an image and telling what each region is. On the top left, we have image classification, which would just say what is in the image overall, like there's a dog here, there's a person here. Next to it, we have on the top right, object detection, where we draw bounding boxes around each object, but we still don't know which exact pixels belong to what. We just know the general area of the objects and what the actual objects are. So on the bottom left, we have semantic segmentation, where we can tell what every pixel is and what class and object it belongs to. So for example, the person, the sheep, the grass, and the dog, and so on. Our project focuses on this bottom task, taking driving images and producing these dense pixel-wise maps known as segmentation maps that are more accurate and more robust for autonomous driving. So within the field of autonomous driving systems, we usually talk about 3 main modules: perception, planning, and control. Our study focus was on the perception module, which is responsible for turning raw sensor data like cameras into real-time understanding of the vehicle's environment and essentially what the vehicle can see. Semantic segmentation is a key part of the perception stack. It separates drivable and non-drivable space, identifies static and dynamic obstacles, and provides context for the environment, like lane marking and sidewalks. These pixel-level maps directly support path planning, lane-level localization, and reasoning about vulnerable road users. However, deploying the segmentation models in safety-critical AD settings has proven difficult. We mostly face 3 main problems. The first one being data constraints due to expensive pixel-perfect labels needed for training, generalizability issues when we encounter new cities or weather conditions, and the computational bottlenecks when training and running models on high-resolution images. Our work is motivated by addressing all 3 at once. So to address the core challenges more clearly, first, data constraints. High-resolution pixel-level annotations are extremely costly and labor-intensive to obtain, since they're traditionally labeled by hand. This type of data has to be at a steady scale, and it must be fine-grained, making this type of data often limited and affecting how often we can retrain and adapt models for new domains. Second, generalizability. Models trained on one city might struggle in another. This can be caused by changes in road layouts, building styles, and especially weather and lighting, like nighttime fog or heavy rain. These can all hurt the performance of the model. We also see class imbalances where common classes dominate. So for example, roads are going to dominate smaller classes and objects like a train or things that we don't often see when driving. So third, computational efficiency. Modern deep segmentation models are heavy. Training on high resolution images and then running them in real time places a large burden on GPUs, especially when trying to deploy on embedded hardware. AD perception needs models that are not only accurate, but also efficient and adaptable. So recent progress in vision foundational models help all three of challenges. These models are pre-trained on large scales on massive images, image corporas, and then adapted to downstream tasks. This presents two key capabilities. First, they often use unsupervised or semi-supervised learning, which reduces reliance on dense manual labels and allows us to leverage large pools of unlabeled data. For example, prior work has shown that pairing foundation models with unsupervised domain adaptation can improve out-of-distribution robustness and reduce label needs. Second, the training provides a strong initialization. When we fine-tune these models for segmentation, they tend to generalize better under distribution shifts and can even support annotation-free or weakly supervised setups. Our work sits right in the space. We take a strong foundational model named SAM and adapt it into a task-specific model that is data efficient, robust, and computationally manageable for AD perception. So the segment anything model, or SAM, I previously mentioned, is a promptable segmentation model released by Meta in 2023. It's trained on a very large data set called SA1B and is capable of zero-shot segmentation given prompts like points, boxes, or masks. This makes it extremely flexible across domains, including ones it was never explicitly trained on. However, SAM is primarily designed for reject segmentation via prompts, not for dense segmentation maps with fixed set of classes like roads, cars, pedestrians, etc. Its architecture and training are optimized for generality and interactiveness rather than for a dense class-specific AD segmentation. Our goal with AD SAM was to bridge that gap. We preserve SAM's powerful global representations while extending and reshaping the architecture so it works as a high-quality, dense semantic segmentation model for autonomous driving scenes. So this leads to a proposed model, AD SAM, which let me summarize the key contributions. First, we introduced a dual encoder architecture, a frozen SAM vid-age encoder for global semantic context and a trainable ResNet50 encoder for local spatial detail. Second, we add a deformable feature fusion model with channel attention to align the recalibrated multi-scale features from both encoders. Third, we design a multi-stage deformable decoder that progressively refines the fuse features from the previous model into accurate segmentation maps. And finally, we define a hybrid loss function that combines 4 key loss functions to target class imbalances, IOU optimizations, and boundary accuracy. So compared to SAM, we achieved a 29 to 48% increase in performance depending on which data we tested it on. And this is a short overview of the AD SAM architecture, which we will be going over now. So first we have the dual encoder vid-age branch. We kept the native SAM image encoder, which is this one, that operates on the 1024 by 1024 inputs. It uses multi-head self-attention to process the image and downsample it by a factor of 16, producing a 64 by 64 grid of embeddings. And each grid cell is 256 dimensions, is a 256 dimensional feature vector. In AD SAM, this encoder was kept frozen. We don't update the weights in order to preserve the reach representations learned from the general large-scale pre-training of SA1B. The resulting feature tensors can be viewed as our global context backbone. It captures large-scale semantics, long-range dependencies, and general visual patterns that transfer well to road scenes. So the second part of our encoder is the ResNet 50 branch. In parallel, we have the ResNet 50 branch, which focuses on local spatial detail. ResNet 50 is initialized with image net weights and produces hierarchical features at 4 different scales. Each of these is passed through a 1x1 convolution to project into a 256-dimensional space, and then linearly interpolated to come in 64x64 resolution. This branch is trained in their setup, so it adapts specifically to AD segmentation, complementing the frozen vid age by sharpening edges, textures, and fine-grained structures like paws, lane markings, and small vehicles. Before we move on, I just want to emphasize each branch's purpose. The SAM vid age branch focuses on global detail, meaning the overall image, while the ResNet 50 branch focuses on the details. And together they provide far more context in the standalone SAM branch. So after that, once we have SAM and ResNet features at matching resolutions and channel sizes, we perform the formable feature fusion. For each scale, we concatenate the SAM and ResNet features and feed them into a deformable convolution. This module learns offset fields and modulation mask to decide where and how strongly to sample the neighborhood. Intuitively, instead of using 3x3 grids, the formal convolutions learn to shift their sampling positions to follow object boundaries or elongated structures that help align features from the 2 encoders, even when their spatial patterns differ due to architecture or pre-training differences. This results in a fused feature map that adaptively combines global transfer context with local convolution detail, which being robust to geometric variation in the scene. So after the formable fusion, we apply channel attention to calibrate the fused features. We take both average pooled and max pooled statistics across spatial dimensions, pass them through a shared 2-layer MLP with a reduced ratio of 16, and then use a sigmoid to produce an attention vector. The vector reweights each channel, strengthening channels that are informative for segmentation and downweighing less useful ones. In practice, this helps the network emphasize features that capture important semantic cues and boundaries, further improving downstream decoder performance. So the fuse and reweight features then enter or multi-stage deformable decoder. We use 3 sequential stages, each consisting of a deformable convolution, followed by a group normalization, GILO activation, and dropout. The decreasing number of groups maintains feature diversity while stabilizing training. Each stage refines the spatial structure and sharpens boundaries, which is crucial for parsing complex urban scenes. Finally, at 3x3, the formable convolution projects the 64-dimensional feature map to 19 semantic classes, giving us the final segmentation logic. So to train this architecture effectively, we use the hybrid loss function that combines 4 complementary loss functions. So our total loss function is a weighted sum of 40% focal loss to address class imbalances by downweighing easy examples and focusing on often underrepresented pixels and classes. Then 30% dice and loss, which directly optimizes region overlap, and 20% loss by softmax loss, a smooth surrogate for IOU, further improving alignment with our evaluation metric. And I'll get into the IOU metric in a different slide. And 10% surface loss, which uses distance transforms to emphasize boundary accuracy. Together, these losses encourage good per-class balance, strong region overlap, and precise edges, while stabilizing optimization. So we evaluated AD-SAM on 2 classic segmentation datasets, Cityscapes and BDD 100K. Cityscape contains high-resolution 1024 by 2048 images from 50 cities with 5,000 finely annotated images split into train, validation, and test samples. It focuses on dense urban European scenes with detailed pixel-wise label for 19 classes. And BDD 100K, on the other hand, is a more diverse driving data set from US cities with 1,000 video clips. And we used a semantic segmentation subset, which is about 10,000 keyframes split into train, validation, and test samples. Its classes were remapped to cityscapes to have a direct comparison between both datasets. So we're using 19 semantic classes in total. After integrity checks, our pipeline retained about 6,000 images from BDD 100K from the original 7,000 of the training subset. So we evaluated the models, all the models that we tested using mean intersection over union, or MIOU for short. For each class, IOU is defined as the true positives divided by the sums of true positives, false positives, and false negatives. It measures how well the prediction mask overlaps with the ground truth. MIOU is simply the average of IOU across all 19 semantic classes. These metrics capture both per-class performance and overall segmentation quality, and they're a standard in semantic segmentation benchmarks. So this is just an example of the metrics, of the IOU metric. We could think of the green square as an object and the red one as another object, or the mask of our object. So we're essentially trying to overlap our red mask over the green object, and it's never going to be perfect. So we're essentially looking at the overlap and calculating a metric of how well it did. So AD-SAM's training was trained on the single NVIDIA GeForce RTX 4090 with 24 gigabytes of VRAM, and we used mixed precision training to save memory and speed up training. All the images were resized to 1024 by 1024 and normalized with ImageNet statistics. In this baseline configuration, we intentionally do not apply extra data augmentation, so many gains come from the architecture and launch designs rather than any sort of heavy augmentation. And we also train with the Adam W optimizer, the standard base learning rate and weight decay, using a cosine annealing schedule for 100 epochs. And the batch size was set very low to only 2 per GPU, because even on a high-end system like ours, the combination of full resolution inputs, the dual encoders, and other deformable modules push VRAM memory limits, which is why the batch size had to be set so low so that the model could run, which just reflects the computational demands of this type of model and semantic segmentation in general. So to evaluate AD-SAM fairly, we compared against 3 baselines: the original SAM model, GSAM, and DeepLab B3. Both SAM and GSAM use the same VidB backbone by default, and GSAM is just an offshoot of SAM, a modified version of SAM. So GSAM operates at a reduced input resolution of 512 by 1024, making it more efficient, but potentially limiting fine-grained detail. Since the resolution is smaller, spatial detailing gets lost. AD-SAM, in contrast, uses the read-H, which is also from SAM, but not used by default, and keeps the full 1024 by 1024 resolution, giving it richer contextual and spatial features. DeepLab B3 with ResNet. DeepLab B3 has a ResNet 101 backbone, and it crops its images to 768 by 768, meaning even more spatial resolution is lost, but it serves as a strong and very popular CNN-based benchmark in segmentation. And we also preserved each model's native configuration, input sizes, and general training setups, so their comparisons are fair and reproducible. So here we show the overall performance on Cityscapes and BDD 100K. On Cityscapes, AD-SAMs achieves about a 68% in MIOU, which is on par to GSAMs, and significantly higher than SAMs and significantly higher than DeepLabs as well. On BDD 100K, which is more diverse and challenging, the differences become much more pronounced. AD-SAM reaches 59%, clearly outperforming GSAM's 46%, and SAM's 40%, and DeepLab's 43%. So while AD-SAM matches GSAM on more structured Cityscapes dataset, it pushes ahead strongly on BDD 100K, indicating that our architecture and loss modifications really pay off on the real-world driving scenarios. Since I mentioned BDD 100K has a lot more to it. There's a lot more weather conditions and whatnot. So this slide looks at training time and scalability across models and dataset. DeepLab B3 is the most time efficient for sure. It has the simplest architecture. It's way lighter than the rest. And GSAM is significantly higher than our version, ADSAM. So while it might not be the fastest, it achieves a balanced trade-off between accuracy and training costs. As training time grows, its training time grows moderately as we increase dataset size, particularly in the mid to high sample regimes, which is consistent with its more complex architecture. So next, let's look at the learning dynamics through the validation MIOU, the curves over 100 epochs, which is what we ran the model for. On both cityscapes and BDD 100K, ADSAM exhibits a steeper early epoch ascent and a smoother convergence profiles than both SAM and GSAM. We're just looking at the SAM variants in this slide. These curves illustrate that ADSAM not only achieves higher final accuracy, but also learns faster and with more stable optimization, which we attribute to the dual encoder design and the hybrid laws. So complementing the validation curves I showed in the previous slides, these are the validation loss trends. ADSAM consistently reaches the lowest validation loss on BDD 100K and shows the most stable convergence across both datasets, which by contrast, SAM and GSAM exhibit higher and more fluctuating losses, especially on BDD 100K. This reinforces the idea that our hybrid loss formulation, combining focal, dyes, loss paths, and surface, helps guide training towards better generalization and more reliable optimization in diverse urban scenes. One of the central questions for AD perception is data efficiency. So how well does a model perform when we only have limited annotated data, since that was one of the main issues I mentioned earlier? So this slide shows AD-SAM and the baselines across varying training set sizes. On Cityscape with 1,000 training samples, AD-SAM reaches about 60% IOU or MIOU, outperforming GSAM's 56%, and SAM's 47%, and DeepLab's 43%. And at full data, AD-SAM remains competitive at about 68% versus or 81.1% versus GSAM's 68.2%. On BDD 100K, AD-SAM reaches 59% at its max dataset sample, significantly higher than GSAM's 46%, SAM's 40%, and DeepLab's 43%, even with only 100 samples. AD-SAM performs competitively, slightly behind DeepLab on Cityscapes, but ahead on BDD 100K. Overall, these results show that AD-SAM is data efficient, particularly in the mid-range 500 to 1,000 data samples, which is critical given the high cost of pixel level annotation. So here we can see the per class performance for AD-SAM across the 19 classes on both datasets. On Cityscapes, AD-SAM achieves very high IOU for common classes like roads, buildings, and the sky, something that's always going to be shown in our data for the most part, and similarly strong scores for vegetation and cars. On BDD 100K, these classes remain strong, showing good generalization to more diverse conditions. Performance in smaller or dynamic objects such as a pole, motorcycle, bicycle, a train, things that might not always be present during driving, is lower, which is a common challenge due to limited pixel footprints and higher class variability. Overall, the per class analysis confirms that AD-SAM produces spatial coherent predictions for both large structural classes and many dynamic classes, while highlighting natural areas for improvement on rare and small objects. So right here, this is some data provided by Cityscapes. On the left is the input image, and on the right is the ground truth. So essentially, the idealized version of our segmentation maps. And here we can see the AD-SAM outputs for this many data samples. So we can see that the more samples we give it, the sharper that the image ends up coming out, the sharper the segmentation map and the objects are shown. So for example, the 100 samples, I like seeing the signs because I feel like these are very geometric shapes that really give us a good view on our model's performance. So at the 100 samples, these triangle signs look very, not very straight, not very perfect. But as we give it more and more data, it starts to make the shape a lot sharper. And again, this is what it should look ideally. So to conclude, we presented ADSAM, a fine-tuned vision foundation model for autonomous driving semantic segmentation. Architecturally, ADSAM integrates a dual encoder, frozen SAM VH plus trainable ResNet 50, deformable fusion with channel intention, and multi-stage deformable decoder. Optimization-wise, it uses a hybrid loss that balances class imbalances, IOU, and boundary accuracy. ADSAM outperforms SAM, GSAM, and DeepLab v3 on cityscapes, and especially on BDD 100K, showing higher MIU, faster and more stable learning dynamics, and strong data efficiency in low and mid-sample regimes. Cross-domain retention analysis further shows that ADSAM provides a good balance between generalization and adaptation flexibility. Overall, results support the idea that targeted architectural and loss level adaptations for foundation models can yield reliable, scalable AD perception without requiring massive amounts of newly and annotated data. So for limitations and possible future work in the field, first, segmentation of small and rare classes remains challenging. The classes I mentioned before, like poles, motorcycles, and trains, suffer from sparse data and small pixel footprints. Addressing this may require class-aware sampling, specialized augmentation, or instance-level refinement. Second, our current setup is a single sensor and single frame. Extending ADSAM to multiple sensor fusion, for example, combining a camera with LiDAR or radar and to temporal fusions across frames could further improve robustness under occlusion and adverse conditions. Third, while ADSAM's computational demands are moderate for a high-end GPU, deploying it in real-time embedded hardware would likely require additional efficiency techniques, such as model pruning, knowledge distillation, or lightweight decoder designs. Addressing these aspects would make ADSAM even more sustainable for real-world autonomous driving pipelines. And that concludes my presentation. Does anyone have any questions?
Well, thank you, Mario. With that, we open the floor for questions. Any? Vagelis, go ahead.
Thank you, Mario. This is great talk, great work. Can you elaborate a little bit on any thoughts you may have? As you touched a little bit on the future work, but how would you start trying to make this deployable so that it can work like on the vehicle itself? Do you have any kind of immediate ideas what you would start with?
Well, the model definitely doesn't work the best on or at all on real-time scenarios. So there would have to be some very large underlying architectural changes to be able to take frame by frame and adapt it in real time.
Would it make sense to like do it near real time, or do you think like basically we would have to kind of distill somehow or change the model, right?
Yeah.
Okay, thank you.
Okay, Luki.
Hello, nice talk. And so when you talk about the accuracy of the segmentation, so you show me the different number of samples, and with the more sample, it has a higher accuracy, right?
Yes.
But I want to know whether you trade off the accuracy and the computation cost, because with the more sample, it costs more computation. Have you already optimized and choose the best number of sample?
Yeah, so in this slide, we can see for each training set size, how long each took. So like we said, for mid-range samples like 500 and 1,000.
Okay. Mm.
Yeah, so that's where we perform
That's
the
the
best.
one, right? But they look like. But does it have any turning point? Like, for example, I see with the more samples, the accuracy increases, always increases. But where's the turning point? and then we do not need to have more sample. I mean, the improvement will be very limited or marginally after a certain number of sample.
Yes.
You
Yeah, so like I mentioned, we are very limited by the amount of data that we have. So it's harder to tell if giving it more data will improve, since we would need to find more and provide more in order to test that.
So okay.
Mario, can I ask you a question? Can you go to that list that you have at the end, like the percentages?
This one?
Okay. Yes. So this is what I don't understand. Like, so you're saying that, hey, the more we see, the better the accuracy, right? So there's well, sidewalk and road and buildings, that's easy. But for example, if I look at traffic lights, right? I mean, the whole point is that you have like so many traffic lights, right? I mean, and the shape is usually it's unique, right? You have a pole that has an angle, right? So why is the percentage so low for traffic light? I can understand, for example, trains, because if you're in an area that a train doesn't pass, right, you're basically not going to have that. But for example, traffic lights, that's something that you would think should have a high percentage.
Yeah, so I think that just goes back to the data limitations. Since both our data sets are just essentially pictures taken from cars driving around different cities, that just means there's more data shown of areas that don't have traffic lights than those that do.
Okay. And is there any way that you can, improve that by feeding it, like you can find a lot of images with traffic lights, right? By feeding that and improving that, because again, like that's like traffic lights is arguably is very important. It's more important, right, than for example, like a train. I understand, right? But see, some of these things, like if we're doing this for driver, right? I mean, you think the ones that should have higher accuracy are the ones that are more risk, right? Like for example, a bicycle, you definitely need to know if it's a bicycle, because that's potentially an accident, or a motorcycle, but also like being able to look at, so vegetation, for example, well, okay, I mean, that's something that is not as important as, I would say, a traffic light. So is there any way where you can fine tune this for the application you're doing?
Yes, we would need to find more similar data to the one we already have, but that just shows more images with traffic lights.
Okay.
But that would definitely improve the overall performance.
Yeah, like with a higher priority, like the weight for different objects.
Yep.
Yes.
Do we have any other questions from the audience? Okay. Well, I would like to take the time to thank all our speakers for their wonderful presentations. They are really, great presentations. And what I would like to also do is hope that the audience will engage. And if you see research that you feel you can help with, or have some suggestions, or even work synergistically, that's the whole point of these webinars. Please make sure that you reach out. If you don't know somebody's contact, reach out to me. I'm more than happy to get you their contacts. But let's keep these conversations. These are really great presentations. The students are doing wonderful, and that's always great to know. But with that, I want to thank everyone. We're exactly at 2, so I want to end this. But thank you for being here, and we will see you in our spring webinar. Thank you all.